Welcome everybody in part 2 of spectroscopy. Today's lesson is about infrared spectroscopy. What is infrared and what is the relationship between the lesson today and the functional group of a compound? First of all, what you have to know about the infrared, it's a radiation that locates after the visible region. So this is your visible region. We have the last one, which is the red color. It comes after the red color. Infra means below red, which means red. So infrared means below red, and this is the explanation of this one here. Now, if you have a molecule, let's say you have CH3 and OH. Okay, and suppose this molecule here is irradiated with an IR radiation. Okay, what happened to this molecule? What happened to the bonds? Just keep in mind, the IR radiation is not that strong radiation. And if the molecule is irradiated by IR, the molecule won't start to fracture, won't start to break, but instead of that, it will start to vibrate. The vibration process or the vibration modes that happen for this molecule, we have two types. The first one is called stretching. The second one is called bending. I'm going to show you how the stretching and bending processes take place. Just keep in mind the stretching here affects only in the length of the bond, and for the bending, it's only the bond angle. How does this one look like? And here it's a stretching mode, and as we can see, the bond length is increasing and decreasing. And here it's a bending process in which the bond angle is increasing and decreasing. For example, if we have a CH bond, when we apply IR radiation on this bond, we will got, let's say, different levels of absorptions if it's like other bond like OH or C double bond O. So they will behave different if we apply the IR radiations on all of these three molecules. So what makes the absorption of IR radiations different? The first one is the length of the bond and the strength of the bond, and finally the mass of each atom. For example, if we have CH and we have CN, which of these two atoms will vibrate faster? You have to keep in mind the bond in here will vibrate faster because it has lighter atoms like hydrogen. So hydrogen is lighter than nitrogen. That's why it vibrates more, and that's why it has a higher frequency. Just keep in mind, if you have a nonpolar molecule, or especially a small molecules that are nonpolar, they won't be able to be detected by IR since the IR is not sensitive to the nonpolar molecules like Cl2 and H2. Once we apply the IR in a molecule, we will end up with a graph that looks like this. It feels and seems weird at the first time, but with the time you'll end up with a lot of things. So the first thing we have to learn, the y-axis represents something called transmittance. And the transmittance describes the amount of absorption that happens, like for IR, like the molecules that absorb IR a lot and the molecules that has no or low absorption of the IR. The x-axis represents something called wave number. The wave number, it's one of the frequency like descriptions, and it represents or it's equal to the reciprocal of the wavelength, and it has a unit of centimeter to the power -1 or inverse centimeter. You can see that this graph is unusual. It starts with a big number and ends up with a smaller number. Okay, the area that we will work on is like above the 1500s. So this is the area that we will work in, and it's called the functional group area, in which we have a functional groups, and this is the area that tells me a lot about the functional groups. But in this area here, it's special for each compound. In this area, it's called fingerprint area. And the fingerprint area provides a lot of details about the specific compound. So we're not working in this area a lot. The main area that we will work in, it's greater than 1500. So this is the workplace for our, for our study. Okay, since we have frequencies, we're going to relate these frequencies to these peaks in here. It means that we are not going to memorize the whole frequencies. Instead of that, you'll be provided with a sheet in the exam that tells you, informs you all of these frequencies, so don't panic if you have no idea how to do that. How can I use this sheet in order to identify the functional group? This is the sheet that you will be provided in your exam. We can see that the wave numbers are responded to specific, bonds. We have stretching vibrations, stretching. All of these guys here are stretching, as we can see. Now, let's take a simple one. For example, if we have a compound like CH3, C double bond O, and CH3, how does the graph look like if we have this compound? Let's draw the IR spectrum. You don't need to draw the IR spectrum in your exam, but I like to start from scratch in order to explain that. First of all, we can see that we have a pureful C double bond O in here, and this is a ketone compound. It has, it has CH bonds. So we have CH bonds, we have C double bond O. These bonds have frequencies and the IR sheet in here that we can see. So C double bond O, where do we have CH? Okay, here we have C double bond O stretching. Okay, ketones. So we are like expecting to have a peak at 1720 to 1700. Okay. And we have another peak that represents the CH, like CH3, which is about like around 3000 something. So technically, we have like 1500s. I don't care about the other things before, Okay, we have C double bond that appears at 1700s to 1720. And this one appears around 3000 or below the 3000. So technically, we can say, okay, we have like 1700s. We are expecting to have a peak at this area, and then we have another peak about like 3000 or below the 3000 by a little, like this. Yeah, so this is an approximate like graph for the IR for this compound. So just keep in mind the intensity, like the transmittance in here, it's so like it has a greater intensity in here for the C double bond O. One thing to know, and C double bond C, if you just look at their graphs in here, okay, you can see this is one here, like it's around 1700, and this one here, it's around 1700. How can I distinguish between the two guys? The intensity, the length of the peak for the alkene is smaller than the length of the C double bond. I want to explain it. For example, if we have a small peak that appears like this, then this peak appears as 1600, so this one here belongs to the C double bond C. But if you have another peak like at 1700, it belongs to the C double bond O. So the difference between the two guys, there's a small difference in their frequencies, but the one that is in shorter like peak belongs to the C double bond C, which means it has a low intensity. The absorbance is not that much in this case. Just keep in mind the peaks when they look like a strong, like almost hit the x-axis, we can say they have a strong intensity and higher absorbance. This bond absorbed IR a lot. One of the most unique things in the IR spectrum is the OH group. The OH, whenever you find it, it could be in alcohols or in carboxylic acids. They have a frequencies about 300. You can distinguish between the alcohols, they have higher frequency than the carboxylic acid, but they look like a broad band. Let me show you. Let's say this is your 3000 and let's say this one here is 3000, like 700. And if we have these peaks, let's say we have peak in here, and we have something like this. Whenever you see any broadband in your IR spectrum, then definitely you have OH group. The OH group could be from alcohol, it could be from carboxylic acids. How can I distinguish whether it's from carboxylic acids or from alcohol? Look at the peak, at what number in here. You can see this peak comes around 3,700, and this is exactly matches the one with alcohol, this one in here. Okay, and this peak represents, if it comes at 1700, it tells you that you have C double bond O. So we can notice and conclude that our compound has a functional group of C double bond O, and it has a functional group of OH. It's not a carboxylic acid. Just make sure it's not a carboxylic acid, because the peak in here comes at 3,700. Okay, now let's jump and take another example, which could be infrared spectrum for this compound. First of all, we can exclude two of these answers immediately. If we look at them here, we have the presence of the OH group, which means we should have a broadband. Now, which of these spectrums have no broadband? It's D and B. So it's either A or C. Okay, we just noticed that we have another functional group, which is alkene C double bond C. And if we just go back again to the ones in here, we're supposed to find C double bond C. We're supposed to have another peak around these guys in here. Yeah, around 1600s and something. So do we have any peak at 1600s in these peaks? Yes, we can see this is a 1500 when you care about it, and this one here is about 1600 something. So this one here represents the C double bond C, and this one represents the OH. Just keep in mind here, these peaks belong to the CH bond. Let's jump to the next one. All right, we have no broadband. It's not alcohol. It's not carboxylic acid. Okay, we can see that we have a peak at 1700. Okay, it's 1700 something, 1700 and something like that. So definitely this one here is C double bond O, and we can see that it has a strong absorption, a strong intensity. It touches the x-axis. Okay, so it's not alcohol, it's not carboxylic acid, it's either C or D. How can I distinguish between aldehyde, which is a propanol, and ketone, which is a propanone? We can see that in aldehyde, you can see the aldehyde has a functional group of this. Okay, the presence of the CH bond appears in aldehyde as this one in here, these peaks. So we have these two peaks for the CH in aldehyde. Definitely this is for the CH in aldehyde group. So definitely the compound is an aldehyde. It's not a ketone. If it's a ketone, then you will end up with nothing like that. It's just only a peak for the CHs. Which of these has a peak at 3,415 and 2,250 infrared? This one here, like, you can cheat it from this sheet. So let's take the first one. We have C triple bond N. Where do we have C triple bond N? Like the nitriles. The nitriles appear as 2,260 appears, yeah. So we can say, yeah, it matches this number in here. And we have an H2. Where do we have an H? The NH thing is appear as a mean, and they have a frequency of 3,500 and something. So this one here belongs to the same range in here. So the answer definitely and obviously it's an A.